The anatomy of a black hole. Hey guys, tonight we are undertaking a journey to the most extreme, the most mysterious, and the most misunderstood destination in the entire cosmos. We are traveling to a place where the laws of physics as we know them break down, where time itself ceases to have meaning, and where the universe has reached its final, most perfect, and most terrifying state. We are going to explore the anatomy of a black hole. But this will not be a journey of fear. We will not be talking about cosmic vacuum cleaners or monsters that devour the stars. Instead, we are going to approach this subject with a sense of quiet wonder. We're going to treat the black hole as a magnificent, silent, and deeply profound piece of cosmic architecture. We will be explorers, cartographers, mapping a landscape that is, by its very nature, invisible. So, before you get too comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what we do here. It truly helps the channel find other sleepless souls like us. And as always, let me know in the comments where you're tuning in from and what time it is. I like to imagine someone in a tiny apartment in Tokyo, another in a cabin in Norway, and someone else in bed at 3:47 a.m. in Milwaukee, wondering how astronomy turned into this. Now, dim the lights if you haven't already. Let the world outside your window fade away. Maybe there's a gentle hum from a fan or the soft whisper of leaves in the breeze. Let's create our own little pocket of tranquility and journey back together across the sands of time. Imagine you are in a small, perfectly safe, and perfectly shielded spacecraft. You have traveled for a very long time to a quiet, lonely corner of the galaxy. Your destination is a place where a truly massive star, a star perhaps 50 times the mass of our own sun, has ended its life in a spectacular supernova. And in its place, it has left behind a ghost, a scar in the fabric of space-time, a black hole. Your first challenge is simply finding it. You cannot see a black hole. It is not a dark object sitting in space. It is an absence, a perfect spherical piece of space-time from which no light can escape. It is the purest black imaginable, a black so complete that it makes the surrounding space, which you once thought of as black, look like a hazy, luminous gray. As you get closer, you begin to see not the hole itself, but its effect on the universe around it. The light from the distant stars behind the black hole is being bent and distorted. Their positions seem to warp and shift as if you are looking at them through the bottom of a thick wine-colored glass. This is gravitational lensing, the first sign that you are in the presence of an immense gravitational power. The black hole is a gravitational phantom, its presence betrayed only by the way it bends the light of others. And then, as you get closer still, you see the first true piece of its anatomy. It is not dark. It is the most brilliant and violent object you have ever seen. It is the accretion disk. This is the core of the black hole, the final, frantic, waiting room for matter that has strayed too close. It is a vast, flat, spinning disk of gas, dust, and the shattered remains of stars, all spiraling inward toward their doom. It is not being sucked in, as the old stories say. It is falling, but with so much sideways momentum that it is forced into a long, slow, orbital decay, like water spiraling down a drain. And this disk is a place of unimaginable violence and incandescent beauty. The material within it, crushed and sheared by the immense gravity, is moving at a significant fraction of the speed of light. The friction, the simple rubbing of gas cloud against gas cloud, is so intense that it becomes the dominant force in this part of the universe. The material is heated to temperatures of millions of degrees, far hotter than the core of our own sun. It glows with a light of ferocious, multicolored brilliance. The outer parts of the disk might glow a dull, angry red. Closer in, it brightens to a brilliant, searing yellow-white, then to a shocking electric blue, and finally, at its innermost edge, it blazes with a light so energetic it is invisible to your eyes, a torrent of X-rays that would sterilize any world for light years around. The accretion disk is a cosmic jewel of breathtaking and lethal beauty. It is the funeral pyre of stars, and it is the brightest object in its corner of the universe. It is a beautiful, terrible warning sign, a luminous swirling moat around a castle of perfect darkness. And from the center of this magnificent, violent jewel, two more anatomical features emerge. Stabbing out from above and below the accretion disk, perpendicular to it, are two colossal, ghostly beams of energy. These are the relativistic jets. The black hole is a messy eater. Not all the material that spirals inward in the accretion disk is destined to fall into the hole. At its innermost edge, the intense, twisted magnetic fields of the spinning disk act like a cosmic particle accelerator. They catch a portion of the superheated matter just before it takes its final plunge, and they channel it, focusing it into two narrow, perfectly collimated beams and blasting it back out into space at nearly the speed of light. These jets are the black hole's voice, a scream of pure energy that can travel for thousands or even millions of light years. They are particle cannons of galactic scale. They will punch clean through the interstellar gas of their host galaxy, carving out immense, empty cavities. They will illuminate distant gas clouds, causing them to glow like ghostly nebulae. They are the most powerful and energetic phenomena in the known universe, after the Big Bang itself. They are the lighthouses of the cosmic abyss. They are beautiful, ethereal, and unimaginably powerful. They are a sign that even from a place of ultimate destruction, a place defined by taking everything in, a startling amount of creative and transformative energy can be unleashed back into the cosmos. So, this is the outer anatomy of our black hole. This is the part we can see, the brilliant, violent, and beautiful accretion disk, the cosmic jewel made of dying stars, and the two powerful, ghostly relativistic jets, the screams of energy that are the black hole's only outward expression. This is the royal court, the chaotic, brilliant, and dangerous world that surrounds the king. But we have not yet approached the king himself. We have not yet reached the place where the true mystery begins. We have not yet come to the border of the abyss. In the center of all this light, all this violence, all this energy, is the true object of our journey, a perfect, calm, and silent sphere of absolute blackness. A place with a name that is both simple and terrifying in its implications. The event horizon. This is the boundary, the point of no return. And to understand what happens there, we must leave the familiar world of light and matter behind and enter a world where space and time themselves begin to unravel. But we will pause our journey here, at the edge of the light, before we take our first tentative step into the dark. We have navigated the chaotic, brilliant, and violent outer court of the black hole. We have witnessed the blazing funeral pyre of the accretion disk and the ghostly, powerful screams of the relativistic jets. Now we must leave this realm of light and energy behind. We must quiet our ship, power down all but our most essential systems, and begin our approach to the true object of our journey. We are going to the border of the abyss. We are approaching the event horizon. From our safe orbital distance, the event horizon appears as a perfect, dark, and silent sphere. It is the hole in the center of the brilliant, swirling donut of the accretion disk. It has a definite size, a physical radius known as the Schwarzschild radius, which is determined solely by the mass of the black hole. A black hole with the mass of our sun would have an event horizon only a few kilometers across. The supermassive black hole at the center of our galaxy has an event horizon that would easily fit within the orbit of Mercury. It is a place, a location in space, and yet it is not made of anything. It is not a surface, it is not a membrane, it is a purely geometric boundary, a threshold. It is the precise point in space where the gravitational pull of the black hole becomes so overwhelmingly powerful that the escape velocity, the speed you would need to travel to get away, becomes equal to the speed of light. And since nothing in the universe can travel faster than the speed of light, this is the point of no return. Anything that crosses this line, a particle of dust, a beam of light, a spaceship, is irrevocably and eternally trapped. Let us begin our thought experiment, the one that has been conducted in the minds of physicists for a century. We will send a probe, a small, instrumented robotic explorer, on a one-way journey across this boundary. We will remain behind in our mother ship, at a safe distance, and watch its progress. Our probe begins its journey, firing its thrusters to leave its stable orbit and begin its long, slow, fatal fall toward the event horizon. From our perspective, as we watch the probe on our view screen, we see the laws of general relativity begin to manifest in their most extreme and bizarre form. The first thing we notice is the effect of gravitational time dilation. As the probe gets deeper into the immense gravitational well of the black hole, we see the clock on board the probe begin to tick slower and slower relative to our own. We see the probe's automated systems moving in slow motion. A diagnostic light that is programmed to blink once per second now blinks once per minute, then once per hour, then once per year. The second thing we notice is the gravitational redshift. The light from the probe's own running lights begins to shift in color. The journey away from the intense gravity is so difficult for the photons of light that they lose energy. They are stretched to longer and longer wavelengths. The probe's bright white lights shift to a dull yellow, then to a deep, ruddy orange, and finally to a sullen blood red. And as it gets closer to the horizon, the light shifts further into the infrared, then into the microwave, and then into the radio, becoming dimmer and fainter and ultimately invisible to our eyes. And then, as the probe reaches the event horizon itself, we would witness the final, ultimate, and most profound illusion. We would see the probe appear to freeze. Its clock would seem to slow to a complete stop. Its forward motion would appear to cease entirely. Its final, dim, red-shifted image would seem to be plastered onto the surface of the event horizon, like a frozen, two-dimensional photograph. From our perspective, in our entire lifetime, in the entire lifetime of the universe itself, we would never ever see the probe actually cross the boundary. Time for the probe, from our point of view, would have stopped. But what would the probe itself experience? Let's switch our perspective. We are now the probe. We are falling. From our own internal reference frame, our clock is ticking normally. A second is still a second. We are not moving in slow motion. We look back at our mothership, and from our perspective, it is their clock that is running impossibly fast. We would see the future history of the external universe flash by at an accelerated rate. And the event horizon? For us, it is not a surface. It is not a wall. It is an invisible, unremarkable line in space. We would sail across it without any sense of impact, without any jolt, without any indication that we had just passed the point of no return. The moment of crossing the event horizon, for the one who is crossing it, is a completely non-event. One moment you are outside, the next moment you are inside. And it is only later that you would realize the terrifying, existential truth of your new location. Because once you are inside the event horizon, the very nature of space and time is fundamentally altered. The rules are rewritten. Outside the black hole, you have a certain freedom of movement. You can move forward and backward in space, left and right, up and down. But you are forced to move in only one direction in time, forward, toward the future. Inside the event horizon, this is reversed. The roles of space and time are, in a very real sense, swapped. Once you cross the boundary, you can no longer move freely in space. The singularity, the point of infinity at the very center of the black hole, is no longer a place in space. It becomes your future. It becomes an unavoidable moment in time. Imagine you are in a river, just before it goes over a massive waterfall. You can still swim left or right toward either bank. But no matter how hard you swim, you cannot stop the current from carrying you downstream toward the inevitable plunge. This is your situation inside a black hole. The singularity is the waterfall. The direction inward toward the center is no longer a direction in space. It has become the direction of the flow of time. All possible paths, all possible futures for any object inside the event horizon end at the singularity. You can fire your rockets in any direction you like, but you are not moving through space. You are simply trying to delay your arrival at a specific, unavoidable moment in your own, now very short future. The fabric of space-time itself is flowing inward, toward the singularity, faster than the speed of light. And you are just a passenger, caught in its inexorable, one-way current. For a very large, supermassive black hole, this journey from the event horizon to the singularity might be relatively peaceful for a time. The tidal forces, the difference in gravitational pull between your head and your feet, might be gentle enough that you wouldn't be immediately torn apart. You would find yourself in a bizarre, warped, and utterly terrifying bubble of reality. If you tried to look up, back toward the event horizon you just crossed, what would you see? You would not see the universe you left behind. You would see a single, brilliant, blue-shifted point of light. The entire history of the external universe, from the moment you cross the horizon to its final, distant end, would be visible to you in that single, infinitely bright point. And if you looked down in the direction you are being carried, you would see nothing but a profound, absolute, and growing darkness. You would be looking at the end of time itself. And as you get closer to the singularity, the tidal forces would become extreme. The gravity at your feet would be so much stronger than the gravity at your head that you would be stretched. A process with a whimsically gruesome name, spaghettification. Your body, your spaceship, the very atoms you are made of, would be drawn out into a long, thin, single-file stream of matter, a final, brief, and violent dissolution before you reach the end. And what is the singularity? What is this place that is not a place, this moment that is the end of all moments? The honest answer is, we don't know. According to Einstein's theory of general relativity, the singularity is a point of zero volume and infinite density. It is a place where all the mass of the black hole is crushed into a geometric point. It is a place where the curvature of space-time becomes infinite. And at this point of infinity, the theory of general relativity, our beautiful and powerful description of gravity, breaks down completely. Its equations produce nonsensical answers. It is the place where the known laws of physics cease to have meaning. It is the end of the line. It is the final, ultimate, and most perfect scar in the fabric of the cosmos. A place where our science, our reason, and our imagination can go no further. It is, for now, a perfect mystery, hidden forever behind the one-way mirror of the event horizon. A place we can describe with mathematics, but can never, ever hope to see. We have journeyed to the edge of the abyss, to the silent, perfect boundary of the event horizon. We have explored the strange, relativistic duality of what it means to fall into a black hole, a journey that is both infinitely long and tragically brief, depending on your point of view. We have confronted the singularity, that point of infinite density where our beautiful laws of physics collapse into a state of profound and humbling ignorance. For decades, this was the accepted picture of a black hole. It was a perfect classical object, as defined by Einstein's general relativity. It was a one-way street in space-time. It had only three properties: its mass, its spin, and its electric charge. Everything else, all the complex information about the star that collapsed to form it, was thought to be lost forever, scrubbed clean from the universe. A black hole, in the famous words of the physicist John Wheeler, has no hair. It is a simple, bald, and eternal object. It is a perfect prison from which nothing, not even information, can escape. But this picture, as elegant as it was, had a deep and troubling problem. It violated one of the most sacred and fundamental laws of the universe, a law we encountered on a previous journey, the second law of thermodynamics, the law of entropy. The second law states that the total entropy, or disorder of a closed system, can never decrease. And yet, a black hole seemed to do just that. You could take a box of hot, disordered gas, a system with very high entropy, and throw it into a black hole. The gas would disappear. And the black hole, a simple, perfect, and seemingly zero entropy object, would just get a little more massive. It looked like a perfect, cosmic crime scene where the evidence of entropy could be hidden forever. It was a direct, glaring contradiction. For years, this paradox troubled the minds of physicists. But in the early 1970s, a young, brilliant, and iconoclastic physicist named Stephen Hawking came along and proposed a solution that would not only solve the paradox, but would completely revolutionize our understanding of what a black hole truly is. He did this by combining the two great pillars of modern physics: Einstein's general relativity, the science of the very large, and quantum mechanics, the science of the very small. He decided to see what would happen if you sprinkled a little bit of quantum uncertainty on the perfect, classical certainty of the event horizon. The result was astonishing. Hawking, through a series of complex and beautiful calculations, discovered that black holes are not, in fact, perfectly black. They must, according to the laws of quantum mechanics, glow. This glow is now known as Hawking radiation. And the way it works is one of the strangest, most beautiful, and most counterintuitive ideas in all of physics. According to quantum field theory, the vacuum of empty space is not truly empty. It is a seething, bubbling, and chaotic foam of virtual particles. For fleeting, almost imperceptible moments, pairs of particles and their antimatter counterparts can spontaneously pop into existence, borrowing a tiny amount of energy from the vacuum, a virtual electron and a virtual positron, for example. In normal, empty space, these pairs exist for only an infinitesimal fraction of a second before they find each other again and annihilate, paying back their energy debt to the vacuum. The vacuum of space is a constant, frenetic dance of creation and annihilation. But what happens if a pair of these virtual particles happens to pop into existence right at the very edge of a black hole's event horizon? Hawking realized that something remarkable could happen. It is possible for one of the particles, say the positron, to fall into the black hole, while the other particle, the electron, escapes into space. The pair is separated forever. The electron that escapes can no longer annihilate with its partner. It can no longer pay back its energy debt to the vacuum. It becomes a real, tangible particle, and to an outside observer, it looks as though the black hole has just emitted a particle. But energy cannot be created from nothing. The escaped electron has a positive energy, and it has just become real. Where did that energy come from? Hawking's brilliant insight was that it must come from the black hole itself. The virtual particle that fell into the black hole is considered to have a kind of negative energy relative to the outside universe. When it falls in, it reduces the total mass and energy of the black hole by a tiny, almost infinitesimal amount. The net result of this bizarre, quantum mechanical process at the edge of the abyss is that the black hole appears to be radiating a steady, slow stream of particles into space. And because it is radiating, it has a temperature. And because it has a temperature, it has entropy. This solved the great paradox. The entropy of a black hole is not zero. It is, in fact, enormous, proportional to the surface area of its event horizon. When you throw that box of hot gas into the black hole, the entropy of the gas disappears, but the surface area of the event horizon increases, and thus the total entropy of the black hole increases by an even greater amount. The second law of thermodynamics is saved. The books of the universe are balanced. But this discovery had an even more profound and mind-bending consequence. If the black hole is radiating particles, and if the energy for those particles is coming from the black hole's own mass, then that must mean that the black hole is losing mass. It must be shrinking. This was a revolutionary, paradigm-shattering idea. Black holes were not, in fact, eternal prisons. They were not forever. They were, in fact, evaporating. Now, this process of evaporation is incredibly, almost comically slow. For a normal stellar mass black hole, the temperature of its Hawking radiation is a tiny fraction of a degree above absolute zero. It is far, far colder than the background temperature of the universe itself. This means that, at the present time, all existing black holes are absorbing far more energy from the cosmic microwave background than they are losing through Hawking radiation. They are all still growing. But in the far, far, far distant future of the universe, when the cosmos has expanded and cooled to the point where the background temperature is almost zero, the slow, patient process of evaporation will become the only game in town. And so, we must travel forward in time again, to an epoch so distant it makes the death of our own sun seem like a recent event. We are in the black hole era of the universe. The stars have all burned out, the galaxies have dissolved. The universe is a cold, dark, and almost empty place, populated only by the last scattered, cooling embers of stellar evolution and the silent gravitational behemoths of the black holes. And here, in the profound, absolute silence of the far future, the black holes begin their long, slow, and lonely death. For a stellar mass black hole, the process will take an unimaginable amount of time, something on the order of 10 to the power of 67 years. A number so vast that if you tried to write it out, the string of zeros would stretch across a small town. For billions and trillions and quadrillions of years, the black hole will slowly, patiently radiate its mass away, one particle at a time. It is the slowest, most inefficient diet imaginable. And as it loses mass, its temperature slowly increases. The evaporation process speeds up. And then, in the final, fleeting moments of its existence, when its mass has dwindled to that of a large mountain, a runaway process begins. The black hole becomes incredibly hot, radiating a torrent of high-energy gamma rays. And in the final second of its life, it releases the last of its stored energy in a final, brilliant, and silent flash of light, a flash with the power of millions of hydrogen bombs. and then it is gone. The prison has dissolved, the singularity has vanished, the scar in space-time has healed. The only thing left is a faint, expanding cloud of ordinary thermal radiation. The black hole, the most permanent and indestructible object in the universe, has evaporated into nothing. This is the ultimate legacy of a black hole, as revealed by the strange and beautiful marriage of relativity and quantum mechanics. It is not an eternal monster. It is a temporary cosmic storage unit. It gathers up matter and energy, holds on to it for an almost infinite amount of time, and then, in the final, dying moments of the universe, it gives it all back, in a final, gentle, and profoundly democratic puff of heat and light. It is the ultimate act of cosmic recycling, a final, beautiful, and complete return to the chaos from which it was born. We have journeyed to the very edge of the abyss and beyond. We have seen how a black hole's immense gravity warps the very fabric of space-time, creating a place where time itself can seem to stop. We have sailed, in our imaginations, across the invisible threshold of the event horizon into a bizarre, inverted reality where the singularity is not a place, but an unavoidable future. And we have witnessed the profound quantum mechanical miracle of Hawking radiation, the discovery that these perfect prisons are not eternal, but are in fact slowly, patiently, and beautifully evaporating. But Stephen Hawking's revolutionary idea, while it solved the great paradox of entropy, gave birth to a new, even deeper, and more troubling mystery. A mystery that strikes at the very heart of what we believe to be the fundamental laws of the universe. This is the black hole information paradox. To understand this, we must first understand a core principle of physics, a concept that is as sacred to a physicist as the conservation of energy. It is the idea that information in a closed system can never be truly destroyed. Information, in this context, doesn't mean the words in a book or the data on a computer. It means the specific, unique, quantum state of every single particle in the universe. The precise position, momentum, and spin of an electron. The exact vibrational state of a quark. This is the universe's ultimate, fundamental data sheet. And according to the laws of quantum mechanics, while you can change this information, you can scramble it, you can hide it, you can never, ever erase it completely. If you burn a book, for example, it seems like the information within it is destroyed. But a physicist would tell you that it isn't. All the information that made up the book, the precise chemical structure of the paper and the ink, is still there, just in a much more disordered, high-entropy form. It is now encoded in the specific trajectory of the smoke particles, the chemical composition of the ash, and the pattern of the heat radiated away into the room. In principle, if you had a powerful enough computer and you could track every single one of those particles, you could reverse the process and reconstruct the book perfectly. The information is not gone, it's just scrambled. This is a fundamental pillar of our understanding of reality. Information is eternal. But a black hole seems to be a flagrant, unapologetic violator of this sacred law. Imagine you have two stars, both with the exact same mass. But one is a simple, pristine star made of pure hydrogen. The other is a complex, old star with a rich and detailed internal structure, perhaps with a system of planets around it, teeming with life, a planet containing libraries filled with the entire works of Shakespeare. Now you collapse both of these stars into black holes. Because they have the same mass, they will form identical black holes. They will have the exact same Schwarzschild radius, the same spin, the same charge. According to the no-hair theorem, they are now completely indistinguishable from each other. The vast, almost infinite amount of unique information that distinguished the star with the Shakespeare-filled planet from the simple hydrogen star has, it seems, vanished. It has been scrubbed clean from the universe, hidden behind the perfect, featureless curtain of the event horizon. For a long time, physicists were able to live with this. They could tell themselves that the information wasn't truly gone. It was just locked away, inaccessible, inside the black hole. But then, Hawking radiation came along, and it turned a troubling problem into a full-blown, terrifying paradox. Hawking's theory suggested that the radiation emitted by a black hole is perfectly thermal. It is a random, chaotic hiss of particles. Its properties depend only on the mass of the black hole, not on what fell in to create it. The radiation escaping from the black hole made of pure hydrogen would be absolutely, completely identical to the radiation escaping from the black hole that swallowed Shakespeare. So when the black holes finally finish their long, slow evaporation and disappear in a final flash of light, what is left? Nothing but two identical, featureless clouds of random thermal radiation. The information is gone, not just hidden, not just scrambled, erased, deleted from the cosmic hard drive forever. The very laws of quantum mechanics, the most successful scientific theory in human history, appear to have been violated. This is the information paradox, and it has been the source of one of the longest and most profound debates in the history of modern physics. It is a war fought with equations and thought experiments, a battle for the soul of reality itself. Is information truly fundamental and eternal, or can a black hole permanently delete a piece of the universe's story? For decades, Stephen Hawking himself was a staunch defender of the idea that information was truly lost. He believed that black holes were a place where the fundamental predictability of the universe broke down. But other physicists argued passionately that this was impossible, that the laws of quantum mechanics must hold true, no matter what. The debate has led to some of the most exotic and mind-bending ideas ever conceived. Perhaps the information is not lost, but is somehow imprinted in a subtle, holographic way onto the surface of the event horizon. The event horizon, in this view, acts like a two-dimensional cosmic hard drive, storing the information of the three-dimensional objects that have fallen inside. This is the holographic principle, the idea that the entire universe might be a kind of hologram, its information encoded on a distant, two-dimensional surface. Or perhaps the information does escape, but in a way that is hidden in the subtle quantum correlations between the particles of Hawking radiation. To our instruments, the radiation looks random. But if you could collect every single particle emitted over 1 trillion years and analyze their entangled quantum states, you might be able to reconstruct the book you threw in at the beginning. The debate still rages. There is no consensus. The black hole, which was once a simple, elegant solution in Einstein's theory, has become the ultimate cosmic puzzle box. It is the place where our two greatest theories of the universe, general relativity and quantum mechanics, meet and go to war. And the fallout from that war is a series of questions that force us to reconsider the very nature of space, of time, and of information itself. And so we complete our anatomical survey. The black hole is not a simple, monstrous object. It is a layered, complex, and deeply paradoxical entity. It has a brilliant, violent, and life-giving core, the accretion disk and the jets. It has a silent, perfect, and illusory boundary, the event horizon. It has a mysterious, unknowable, and law-breaking heart, the singularity. And it has a strange quantum mechanical soul that allows it to glow, to have a temperature, to have entropy, and to, over the course of an almost infinite amount of time, slowly, beautifully, and completely die. It is the most perfect and the most paradoxical object in the universe. It is a place of absolute simplicity and of infinite complexity. It is an end, but it is also, through its recycling of matter and energy, a beginning. As our imaginary spacecraft pulls away, as the brilliant jewel of the accretion disk and the perfect sphere of darkness shrink into a single, distant point of light, we are left with a feeling of profound and humbling awe. We have journeyed to the absolute limit of our understanding. We have looked into the face of a physical infinite, and we have found that it is not a place of answers, but a place of the deepest and most beautiful questions. The black hole is a cosmic mirror. In its perfect, dark, and silent surface, we see the reflection of our own intellectual limits. We see the boundaries of our own knowledge. And we are reminded that the universe is not just stranger than we imagine. It is stranger than we can imagine. And so our journey into the perfect darkness comes to an end. We have dissected the anatomy of the most extreme object in the cosmos, and we have found that it is not an object of pure destruction, but a place of profound and beautiful mystery. It is a testament to the strange, elegant, and often contradictory laws that govern our universe. Galileo's telescope. Now, we are not traveling in a spaceship of metal and wire, but in a different kind of vessel. A vessel of wood and leather and meticulously polished glass. We are journeying back in time to the dawn of modern astronomy, to a specific room in a specific city on a series of cold, clear nights in the winter of 1609. We're going to stand beside Galileo Galilei. We're going to look through his telescope, and we're going to try and feel, just for a moment, what it was like to be the very first human being to see the universe as it truly is. This is a story about more than just a scientific discovery. It is the story of a man, a new and dangerous idea, and the moment the heavens were torn down and rebuilt forever. Imagine you are in Padua, in the Republic of Venice. The year is 1609. The night is cold. The air in your study smells of old paper, beeswax from the candles, and the faint, lingering aroma of the wine you had with your supper. You are Galileo Galilei. You are 45 years old. You are not yet the great, legendary figure of the history books. You are a man, a brilliant, ambitious, and often frustrated mathematics professor at the university. Your life is a constant struggle. You are perpetually short of money. You have a family to support, 2 daughters and a son, all born out of wedlock, a quiet, personal scandal you must manage. You have academic rivals who scoff at your ideas. You are a man of immense talent and even greater pride, living in a world that does not yet fully appreciate you. But tonight, you are not thinking about your debts or your rivals. You are thinking about the sky. Step outside with you into the cool, damp air of your garden. Look up. What do you see? What is the universe to you in 1609? It is not the vast, empty, and infinite space we know today. To you, the universe is a place of profound, divine, and perfect order. It is a set of nested, crystalline spheres, like a series of transparent Russian dolls, all centered on one single unmoving point, the Earth. Your Earth is stationary. It is the center of everything. It is the heavy, corrupt, and changeable heart of the cosmos. And around it, embedded in these great invisible, rotating spheres, are the celestial bodies. The first sphere carries the moon. Then comes Mercury, then Venus. The fourth, great sphere carries the sun itself, which dutifully and perfectly circles your Earth once a day. Then come the spheres of Mars, Jupiter, and Saturn. And finally the outermost sphere, the primum mobile, the sphere of the fixed stars, a great black star-dusted canopy that encloses the entire known universe. This is your reality, and it is beautiful. It is a universe that is logical, that is harmonious, that has a place for everything, and everything in its place. And most importantly, it is a universe that is divided into 2 distinct realms. There is your world, the sublunary world, the Earth, a place of change, of decay, of life, and of death. A place made of the 4 imperfect elements, earth, water, air, and fire. And then there is the heavens, the superlunary world. Everything from the moon outwards, this is a realm of perfection. It is unchanging. It is eternal. The celestial bodies are not made of rock and dirt. They are made of a perfect 5th element, the quintessence, or the ether. They are not worlds. They are perfect, polished, luminous spheres, perhaps translucent, gliding in perfect circular orbits, moved by the will of God. The moon is not a cratered rock. It is a smooth, ethereal, and immaculate globe of light. This is not just a scientific model. It is a matter of profound theological and philosophical importance. It is the worldview of Aristotle and Ptolemy, sanctioned and sanctified by the authority of the Church. It is the intellectual bedrock of your entire civilization. To question this order, to suggest that the heavens are not perfect, to suggest that the Earth is not the center of all things, is not just to commit a scientific error. It is to challenge the very word of God. It is a dangerous and potentially heretical act. And you, Galileo, believe in this universe. You are a devout man. You see the hand of God in its perfect geometric harmony, but you also have a restless, curious, and practical mind. And earlier this year, you heard a rumor from Holland of a new invention, a spyglass, a tube with a lens at either end that could make distant objects appear closer. It was a novelty, a toy for the wealthy. But you, with your practical mind, immediately grasped its potential. You did not think of the stars. You thought of commerce and of war. You knew that if you could build a better version of this device, you could sell it to the Doge, the leader of the great naval power of Venice. A telescope would allow Venetian sailors to see enemy ships hours before they could be seen themselves. It was a weapon. It was a tool of immense strategic and commercial value. And so, you set to work. Not as an astronomer, but as an inventor, an entrepreneur. You teach yourself the art of lens grinding, a difficult and painstaking craft. You spend long, frustrating hours in your workshop, hunched over a piece of glass, the gritty, scraping sound of the grinding powder filling the air. You ruin dozens of lenses, but you persist. You learn the secrets of the curves, the focal lengths, and you build a spyglass that is not just a novelty. It is a precision instrument, far more powerful than the Dutch original. You present your invention to the Venetian Senate. You take them to the top of the bell tower in St. Mark's Square, and you let them look through it. They see ships on the horizon, 2 hours before their sails are visible to the naked eye. They are astonished. They are delighted. They double your salary and grant you lifetime tenure at the university. Your financial troubles, for the moment, are over. You have succeeded. You are a celebrated inventor. And then one night, in the autumn of 1609, driven by that restless, insatiable curiosity, you do something that no one has ever thought to do before with an instrument of this power. You do something that will change the world forever. You take your new, powerful telescope, your spyglass, and you turn it away from the sea. You point it up at the sky. Your first target is the most familiar of the celestial objects, the one that was supposed to be the very definition of heavenly perfection, the moon. You bring the eyepiece to your eye. The image is blurry at first. You adjust the focus. The ghostly, shimmering disk of the moon swims into view. And you gasp. The breath catches in your throat. Your heart begins to pound. Because the moon you see in your telescope is not the moon of Aristotle and Ptolemy. It is not a smooth, polished, perfect, ethereal sphere of quintessence. It is a world. You can see with a clarity that is shocking that its surface is not smooth. It is rough. It is uneven. It is covered in vast, dark patches that look for all the world like seas. And most shocking of all, you can see mountains, real mountains with sharp, jagged peaks, and you can see valleys, and you can see vast circular craters with high, steep walls. You watch, night after night, as the Terminator, the line between the sunlit and the dark part of the moon, creeps across its surface. And you see the peaks of the lunar mountains catch the first rays of the rising sun, shining like brilliant points of light in the surrounding darkness, just as the peaks of the Alps on Earth catch the dawn. You can even, using your knowledge of geometry, measure the shadows they cast, and you calculate, with a sense of dizzying awe, that some of these mountains on the moon are even taller than the tallest mountains on Earth. This is not a perfect heavenly orb. This is a place that is scarred and cratered and mountainous, a place that is, in its fundamental nature, shockingly, heretically, Earth-like. You sit there in the cold, dark garden, the telescope feeling impossibly heavy in your hands. You do not yet know it, but in this single, breathtaking moment, you have just thrown the first stone that will eventually shatter the crystal spheres of the ancient cosmos. You have taken the perfect, incorruptible heavens, and you have brought them down to Earth, and you are just getting started. The sky is full of secrets, and you, Galileo Galilei, are the first human being with the key to unlock them. The revelation of the moon's true nature, a scarred, mountainous, and profoundly Earth-like world, has shaken you to your core. The perfect, polished sphere of the ancient philosophers has been shattered, replaced by a place of rugged, tangible reality. For weeks, you spend every clear night in your garden, your eye pressed to the cold, brass eyepiece of your telescope, sketching what you see. You draw the craters, the mountains, the vast, dark plains you call Maria, or seas. You are no longer just an inventor. You have become an explorer, a cartographer of a new, undiscovered world. But the moon is just the beginning. Your curiosity, now a raging fire, pulls your gaze deeper into the cosmos. On those same cold, clear nights, after you have finished your lunar observations, you turn your telescope to other parts of the sky, to other familiar ancient lights. You point it toward that faint, cloudy, luminous river of light that arcs across the night sky, a feature that has been a source of myth and wonder for every culture on Earth, the Milky Way. To your naked eye, it is a soft, ethereal, and continuous band of light, a celestial cloud. The Greeks believed it was a spurt of milk from the breast of the goddess Hera. The Cherokee saw it as the trail of a corn-thieving dog. But no one knew what it truly was. You point your telescope at it, and the sight that greets you is even more astonishing in its own way than the mountains of the moon. The cloudy, milky band of light dissolves. It shatters into 1,000 100,000, a million individual points of light. It is not a cloud, it is a swarm, a vast, dense, and unimaginably distant collection of individual stars. Stars that are too faint and too crowded together for the naked eye to resolve. The universe has just become, in a single, breathtaking instant, immeasurably larger. You sweep your telescope along the band of the Milky Way, and everywhere you look, it is the same, an ocean of stars. You point it at the supposedly nebulous objects, the fuzzy patches of light in constellations like Orion and Praesepe. And they too, under the power of your lens, resolve into dense, brilliant clusters of individual stars. You feel a sense of vertigo, a feeling of being a tiny, insignificant creature looking out into an infinite, glittering ocean. The cozy, enclosed, and knowable universe of the crystalline spheres is beginning to feel less like a divine hall and more like a small, self-imposed prison. You are beginning to realize that the universe is not just more complex than you had imagined. It is vastly, terrifyingly, and beautifully more crowded. You are a man who has lived his whole life in a small, familiar valley, and you have just climbed to the top of the highest peak and seen, for the first time, the endless rolling expanse of the world beyond. The implications are profound. If there are this many stars, countless more than the 1,000 or so that the ancients had cataloged, then what are they? Are they just decorative lights on the outer wall of the cosmos? Or are they suns? Suns like our own, perhaps with their own planets, their own worlds, their own life? This is a dangerous thought, a heretical thought. The idea of a plurality of worlds was a concept that the Church had condemned. And yet, as you look through your telescope at the infinite glittering river of the Milky Way, the thought is unavoidable. The universe has suddenly become pregnant with a billion new possibilities. But your greatest, most world-changing discovery is yet to come. And it will arrive, as great discoveries often do, not with a sudden, dramatic flourish, but with a quiet, patient, and methodical series of observations. In January of 1610, you turn your telescope toward the planet Jupiter. To your naked eye, it is one of the brightest wandering stars in the sky, a brilliant, steady point of light. You are expecting to see it as a small, perfect disk. On the night of January 7th, you point your telescope at the planet, and you see it. A small, clear, circular disk, more defined than a star, but still just a small globe of light. But you notice something else, something you hadn't expected. Near the planet, in an almost perfectly straight line, are 3 small, faint, and seemingly insignificant stars. You make a note of it in your journal, a simple, dispassionate observation. You are a careful and methodical man. You draw a small sketch, a circle for Jupiter, and 3 small asterisks to one side. You assume they are just background stars, part of the vast, newly discovered multitude. A celestial coincidence. But you are a creature of habit and of curiosity. The next night, January 8th, you decide to look at Jupiter again, and you are immediately confronted with a puzzle. The 3 little stars are still there, but they have moved. They are now all on the other side of Jupiter. This is strange. You know that Jupiter is moving against the background of the fixed stars, but its motion is slow, stately, taking years to cross the sky. For these stars to have changed their position so dramatically relative to the planet overnight is inexplicable. The planet, it seems, has moved the wrong way. It has gone from being to the west of these stars to being to the east of them. You are confused. Perhaps you think you have made a mistake. Perhaps the astronomical tables you are using are incorrect. Perhaps your own calculations of Jupiter's motion are flawed. You are a scientist. Your first instinct is to doubt yourself, not the heavens. You wait for the next clear night. The sky is cloudy for the next 2 days. The frustration is immense. You are a man who has just been given a glimpse of a profound secret, and now the curtain has been drawn. Finally, on January 10th, the sky is clear again. You rush to your telescope, your heart pounding with anticipation. You point it at Jupiter, and your confusion deepens. This time, you see only 2 of the little stars, not 3. And they are both on the eastern side of the planet. Where did the 3rd one go? You assume it must be hiding behind Jupiter, eclipsed by the planet's great disk. This is the moment. This is the turning point. A lesser man, a less patient man, might have dismissed these observations as a strange, inexplicable anomaly. But you, Galileo, are a true scientist. You are driven by a need to understand, and you decide to do something simple, yet revolutionary. You decide to watch. You will observe Jupiter every single clear night, and you will meticulously, dispassionately record the positions of these strange, dancing little stars. Night after night, you return to your cold garden. You sketch the positions of the stars in your journal. January 11th, 2 stars to the east. January 12th, 2 stars to the east, 1 to the west. January 13th, 4 stars. A new one has appeared. All 4 are now visible, forming a perfect, delicate, and beautiful string of pearls, threaded through the great glowing orb of Jupiter. And as you look at your own drawings, at the collected data from a week of patient, careful observation, a new, radical, and world-shattering idea begins to form in your mind. These are not fixed stars. The only way to explain their strange, regular, and predictable dance, their nightly shift in position, their periodic disappearances and reappearances, is to conclude that they are not in the background at all. They are in the foreground. They are not stars. They are moons. They are celestial bodies that are physically tied to Jupiter, moving with it and circling around it. You are not looking at a static picture. You are looking at a solar system in miniature. You sit there, in the profound silence of the night, the weight of your discovery settling over you. It is a moment of pure, terrifying, and exhilarating intellectual vertigo. For in this single, brilliant insight, you have just smashed one of the fundamental pillars of the old cosmos. The ancient Aristotelian universe, the universe of the Church, demanded that everything in the heavens must circle the earth. The earth was the center of all motion. It was a physical and a theological necessity. And yet, here in the eyepiece of your telescope is the proof. The undeniable observational proof that this is not true. Here are 4 celestial bodies, 4 stars, that are clearly, obviously, and indisputably orbiting Jupiter. If these 4 moons can orbit Jupiter, then it is no longer necessary for everything to orbit the Earth. You have found a new center of motion in the heavens. You have discovered a flaw in the perfect, divine, and earth-centered clockwork of the cosmos. And more than that, you have provided the first, powerful piece of observational evidence for a new and deeply heretical model of the universe. The model proposed by the Polish astronomer Nicolaus Copernicus nearly 70 years earlier, a model that suggested that the Earth was not the center of the universe, that the Earth, in fact, was just another planet, and that it, along with all the other planets, orbited the Sun. The Copernican model had always been an elegant, but purely mathematical, curiosity. There was no physical proof for it, but you, Galileo, have just found it. You have found a model of the Copernican system, a tiny, working replica, playing itself out every night in the sky around the planet Jupiter. You know in this moment that your life will never be the same. You are no longer just a mathematics professor. You are the sole possessor of a dangerous and magnificent new truth. You have seen with your own eyes something that could and would turn the entire world upside down. The question now is, what will you do with it? The nights of January 1610 are the fulcrum upon which your entire life, and in many ways, the entire history of science, will turn. You are no longer just an observer. You are the custodian of a secret that feels like a burning coal in your hands. You are in possession of a truth that fundamentally contradicts the established wisdom of 2,000 years and the sacred doctrine of the Holy Church. The silent, dancing moons of Jupiter have whispered a revolution in your ear. For weeks, you continue your observations, your journal filling with meticulous, nightly sketches of the 4 new worlds. You track their orbits, you measure their periods, you watch them disappear behind the great disk of Jupiter and reappear on the other side. You give them a name in a stroke of brilliant political maneuvering. You call them the Medicean stars in honor of the powerful Medici family, your former patrons, whose favor you are desperately trying to win to secure a more prestigious and better-paying position at the court in Florence. You are a revolutionary, but you are also a pragmatist. You understand that a truth needs a powerful protector to survive. The question that now consumes you is no longer, what am I seeing, but what do I do? You are a devout Catholic. You believe in God. You believe the Bible is the Word of God, but you also believe in the evidence of your own eyes. Your telescope is not a tool of heresy. You see it as a new divine instrument, a second revelation that allows you to read God's other book, the book of nature. And you believe that the two books, Scripture and nature, cannot contradict each other if they are both from the same divine author. If there is a contradiction, it must be in our human interpretation of the words, not in the facts of the world. This is a subtle and dangerous line of reasoning. You could keep this discovery to yourself. You could continue your quiet, nightly observations, filling your private journals with these profound secrets, and avoid the inevitable conflict that their publication would bring. It would be the safe path, the prudent path. But you are Galileo Galilei. You are a man of immense pride, of fierce ambition, and of a deep, unshakable, and ultimately dangerous conviction in the power of reason and evidence. You are not a man who keeps secrets. And so, with a speed that is breathtaking, you decide to publish. You rush your findings into a small, explosive book titled Sidereus Nuncius, The Starry Messenger. In it, you lay out your discoveries in clear, accessible, and elegant prose. You describe the rugged, mountainous surface of the moon. You speak of the infinite, countless stars that make up the Milky Way. And most importantly, you describe your nightly observations of the four moons of Jupiter, complete with your own detailed drawings. The book is a sensation. It is a thunderclap that echoes across the intellectual landscape of Europe. It is published not in the dense academic Latin that would limit it to a small circle of scholars, but in a more accessible style that can be read and understood by any educated person. You become, overnight, the most famous and most controversial scientist in the world. The reaction is a firestorm of excitement, disbelief, and outrage. Many are thrilled. They see you as a new Columbus, an explorer who has opened up a new, undiscovered continent in the heavens. Telescopes based on your design are built across Europe, and other astronomers rush to confirm your findings. And they do. The mountains of the moon are real. The moons of Jupiter are real. You are celebrated. You are lauded. You achieve your goal of securing the prestigious post of chief mathematician and philosopher to the Grand Duke of Tuscany in Florence. But for every supporter, there is a skeptic. And for every skeptic, there is an enemy. The established philosophers, the academics whose entire careers have been built on the bedrock of Aristotle, are outraged. You, a mere mathematician, a tinkerer with lenses, have dared to challenge the great master. They refuse to even look through your telescope, dismissing it as a conjurer's trick, a device that creates illusions. They argue that if God had intended for man to see these new stars, he would have given us stronger eyes. They write scathing pamphlets ridiculing your claims. The battle is joined, but it is not yet a battle with the church. It is a battle with the academic establishment. It is a battle of ideas, of evidence versus authority. And you, Galileo, are a brilliant and formidable fighter. You are a master of rhetoric, of debate. You write witty, sarcastic, and often deeply insulting replies to your critics. You do not suffer fools gladly, and you see fools everywhere. You are winning the argument, but you are not winning friends. Your pride, your greatest strength, is also becoming your greatest liability. And then, later that same year, you make the discovery that will seal your fate. You turn your telescope to the planet Venus. According to the old, Ptolemaic, Earth-centered model of the universe, Venus orbits the Earth. It is always located somewhere between the Earth and the Sun. If this were true, then Venus, like our own moon, should show phases. But because of its position, it should only ever show a crescent phase or a new phase. It should never, ever be possible to see a full or a gibbous, more than half-full Venus from Earth. The Copernican, sun-centered model, on the other hand, makes a completely different and very specific prediction. In this model, Venus orbits the Sun, and at times it is on the far side of the Sun from the Earth. If this were true, then Venus should show a full range of phases, just like the Moon. We should be able to see a crescent Venus, a half Venus, a gibbous Venus, and a nearly full Venus. For centuries, this had been a purely theoretical argument. The phases of Venus are completely invisible to the naked eye, but they are not invisible to your telescope. You begin to observe Venus night after night, and you see it with your own eyes. You see a tiny, perfect crescent Venus. And over the course of several months, you watch with a sense of growing, triumphant, and terrifying certainty as that crescent waxes, it grows into a half Venus, and then it grows into a gibbous Venus. This is it. This is the smoking gun. The moons of Jupiter prove that not everything orbited the Earth, but the phases of Venus prove something far more profound. They prove, with the certainty of direct observational geometric fact, that Venus orbits the Sun. And if Venus orbits the Sun, then the entire elaborate and beautiful clockwork of the Ptolemaic Earth-centered universe is a lie. This is no longer a matter of academic debate. This is a direct, physical refutation of the established, church-sanctioned model of the cosmos. The choice is now stark and unavoidable. You can believe the evidence of your own eyes, or you can believe the authority of the ancient texts. You cannot do both. You know the danger you are in. You have heard the stories of Giordano Bruno, the philosopher who was burned at the stake just a decade earlier for his heretical ideas, including the idea of a plurality of worlds. But you are a man of unshakable faith in your own observations, and you are perhaps a man who has become a little too confident in his own fame and the protection of his powerful patrons. You begin to champion the Copernican cause, not just as a mathematical hypothesis, but as a physical reality. You write letters, you give lectures, you engage in public debates. You are no longer just an astronomer, you have become an advocate, a crusader for a new cosmology. And in doing so, you finally attract the attention of the one institution you cannot afford to make an enemy of. Your academic rivals, seeing an opportunity to destroy you, begin to whisper in the ears of the cardinals in Rome. They tell them that this arrogant mathematician from Florence is not just challenging Aristotle, he is challenging the Holy Scripture itself. They point to passages in the Bible that seem to support an earth-centered cosmos, like the story of Joshua, who commanded the sun, not the earth, to stand still. The gears of the Roman Inquisition, a machine designed to detect and extinguish the faintest spark of heresy, begin to turn. Slowly, quietly, and inexorably, they begin to turn towards you. You have armed your enemies with the evidence they need, and your own pride, your own refusal to back down, your own sarcastic and dismissive attitude toward your opponents has alienated many who might have been your allies. The stage is being set for the great, tragic, and inevitable confrontation between the man who had seen the heavens as they truly are and an institution that was not yet ready to let go of the world as they believed it should be. The telescope, your instrument of liberation and discovery, is about to become the source of your downfall. The year is now 1616. The initial, brilliant flash of your discoveries has faded, replaced by the long, grinding, and dangerous work of defending them. The battle has moved from the academic halls of Padua and Florence to the shadowy corridors of power in Rome. You are no longer just debating with professors. You are now entangled with princes of the church. You travel to Rome, confident in your arguments, confident in the truth of your observations. You believe that if you can just explain the evidence clearly, if you can show these intelligent, educated men the moons of Jupiter, the phases of Venus, they will see what you have seen. They will understand that the Copernican system is not a heresy, but a more beautiful and more accurate description of God's creation. You believe in the power of reason. This is your greatest miscalculation. You are a scientist, confronting a political and theological institution. You believe you are in a debate about the facts of the natural world. But the men of the Inquisition believe you are in a struggle for the soul of Christendom. For them, this is not about the orbits of the planets. It is about authority. The authority of the church to interpret the Word of God. And in the Bible, Joshua commands the sun to stand still, not the earth. To them, the case is that simple. To contradict the literal interpretation of Scripture is to challenge the foundation of their entire worldview. The first blow comes swiftly. The Holy Office of the Inquisition formally condemns the Copernican theory. The works of Copernicus are placed on the index of forbidden books. The doctrine that the sun is the center of the world and that the earth moves is declared foolish and absurd in philosophy and formally heretical. You are not punished, not yet. You are a famous and well-connected man. Instead, you are summoned before the powerful Cardinal Bellarmine, the same man who had presided over the trial of Giordano Bruno. In a quiet, private meeting, you are formally warned. you are admonished to abandon the Copernican theory. You are forbidden to hold, teach, or defend it in any way, orally or in writing. You are faced with a terrible choice: defy the order and risk the fate of Bruno, or obey and live a life of intellectual silence, a liar to your own conscience. You choose a third path, a path of careful, calculated, and ultimately arrogant compromise. You agree to obey the letter of the injunction. You fall silent on the Copernican issue. For years, you return to your work on other, safer areas of science. You study mechanics, motion, magnetism. But the truth of the heavens, the truth you had seen with your own eyes, still burns within you. And then in 1623, a new pope is elected. He is Cardinal Maffeo Barberini, who takes the name Urban VIII. And he is a friend, he is an admirer of yours, an intellectual, a man who has written poems in your honor. You believe you now have a powerful ally in the Vatican. You believe the intellectual climate is changing. You believe you have found a loophole. You decide to write your masterpiece. A great book that will, you think, cleverly and subtly, defend the Copernican system without technically violating the injunction. You will not hold or defend it as a fact. You will present it as a mere hypothesis. The book is titled Dialogue Concerning the Two Chief World Systems. It is not a dry scientific treatise. It is a brilliant, witty, and engaging play, a conversation between three characters. There is Salviati, a brilliant, quick-witted scholar who represents your own views and argues for the Copernican system. There is Sagredo, an intelligent and open-minded layman who is slowly persuaded by Salviati's arguments. And then there is Simplicio, Simpleton, a bumbling, dogmatic, and slightly dim-witted defender of the old, Ptolemaic, earth-centered view. This is your fatal act of hubris. You have been warned not to defend Copernicus, and you have written a book that is, in its every fiber, a passionate, eloquent, and devastatingly effective defense of Copernicus. And worse, in the character of Simplicio, you have created a caricature of your opponents. You put the arguments of the Pope himself, the very words of your supposed friend and protector, Urban VIII, into the mouth of a fool. When the Pope reads the book, he is not amused. He is enraged. He feels betrayed, ridiculed, and publicly humiliated. Your powerful protector becomes your most implacable enemy. The full, terrifying weight of the Roman Inquisition now descends upon you. In 1633, you are summoned to Rome to stand trial for heresy. You are now an old man, nearly 70, frail and in poor health. The journey is arduous. You arrive in Rome not as a celebrated scientist, but as a prisoner. The trial is a foregone conclusion. It is not a search for the truth. It is an act of political and theological theater, designed to make an example of you. You are shown the instruments of torture. You are threatened. Your spirit, once so fiery and defiant, is finally broken. On June 22, 1633, in a large hall in the convent of Santa Maria sopra Minerva, you are forced to your knees. Dressed in the white shirt of a penitent, you read aloud from a prepared confession. You, Galileo Galilei, a man who had seen the moons of Jupiter, a man who had watched the phases of Venus, a man who knew, with a certainty born of direct observation, that the earth moved, are forced to say the words. You are forced to abjure, curse, and detest the great error and heresy of the motion of the earth. You are forced to declare the truth you had discovered to be a lie. It is the most famous and the most heartbreaking moment of surrender in the history of science. Legend has it that as you rose from your knees, you muttered under your breath, "Epper si muove," and yet it moves. It is a beautiful story, but it is almost certainly not true. To have said such a thing would have been an act of suicide. In that moment, you were a broken man, saving your own life. Your life is spared, but you are sentenced to be a prisoner for the rest of your days. You are placed under permanent house arrest in your villa outside of Florence. You are forbidden to publish, forbidden to teach, forbidden to have visitors without the permission of the Inquisition. You are a giant, now in a cage. And so, you spend the last decade of your life in a strange, quiet twilight. You are a legend, a martyr, the most famous scientist in the world, yet you are a prisoner in your own home. Your health fails. Your eyesight, the very sense that had opened up the heavens, begins to fade. The man who had seen farther than any human in history is now going blind. It is a final, tragic, and poetic irony. But you do not stop working. In your final years, in secret, you write your last and perhaps your greatest book. It is not about the heavens, it is about the laws of motion. It is the foundation upon which Isaac Newton would later build his own grand synthesis. You dictate the final chapters to your students after you have gone completely blind. You die in 1642, still a prisoner of the church, but you have already won. You won because the truth you had unleashed could not be imprisoned. Your books, though banned by the church, were smuggled out and published across Protestant Europe. The telescope could not be uninvented. The moons of Jupiter could not be unseen. The phases of Venus continued their silent celestial dance, an eternal, irrefutable argument against the old order. You did not just discover new objects in the sky, you discovered a new way of knowing. You taught us that the book of nature is written in the language of mathematics and can be read with instruments. You taught us that authority is no substitute for evidence. You replaced a universe of divine perfection with a universe of physical laws. Your trial was not the defeat of science. It was the moment that science as a way of knowing was truly born. It was a declaration of independence for the human mind. So, as you lie in your bed in the quiet of the night, think of that old blind man, a prisoner in his own house, his mind still soaring through the cosmos he could no longer see. He was a flawed and difficult man. He was proud, arrogant, and often reckless. But he was also a man of immense courage, a man who trusted the evidence of his own eyes above all else, even when it cost him his freedom. He gave us the modern universe, and his story is a quiet, powerful reminder that the journey to the truth is often a long, difficult, and lonely one. But the stars, in their silent, steady, and unwavering light, will always, in the end, have the final word. And so our journey ends, not in a garden in Padua, but in a quiet villa, with a man who had seen the universe and paid the price. Galileo's story is a profound and timeless lesson about the conflict between new discoveries and old beliefs, and the courage it takes to see the world not as we wish it were, but as it truly is. Jupiter, the great protector. Hey guys, now we're journeying out beyond the rocky inner planets, past the great, dusty expanse of the asteroid belt, to the realm of the giants. Our destination is the undisputed king of our solar system, a world so vast it could swallow every other planet whole and still have room to spare. We're going to be talking about Jupiter. But this isn't just a story about its swirling storms, its colorful cloud bands, or its multitude of moons. This is the story of a silent guardian. We are going to explore the profound and often violent role that Jupiter has played in the history of our solar system, and how its immense gravitational presence has acted as a shield, a bouncer, and a protector for our small, fragile, and incredibly lucky planet. Imagine you are in a small, sturdy spacecraft, drifting in the quiet, cold space just beyond the orbit of Mars. You are in the heart of the asteroid belt. Around you, in the sun-dusted darkness, is a swarm of millions of rocks, ranging in size from tiny pebbles to mountain-sized planetoids. This is the rubble of creation, the leftover building materials from the formation of our solar system, a vast, orbiting junkyard of primordial rock and ice. From here, if you look back toward the sun, you can see the inner solar system. You can see the faint, reddish light of Mars, the brilliant, star-like beacon of Venus, and if you look very carefully, a tiny, pale blue dot, Earth. It looks small, fragile, vulnerable. Now turn your gaze outward, away from the sun, and you see it. It is not a point of light, it is a disk, a vast, majestic, and intimidating presence that dominates this entire region of space. It is Jupiter. Even from this great distance, its scale is breathtaking. It is a colossal striped globe of swirling pastel colors, creams, ochres, ambers, and rust reds. You can see the great parallel bands of its clouds, rivers of ammonia and water ice, thousands of miles wide, flowing in opposite directions. And you can see, even from here, the single, most famous feature in the entire solar system. A baleful, deep red, unblinking eye staring out into the cosmos. The Great Red Spot, a storm so vast it could swallow the Earth 3 times over. A storm that has been raging, uninterrupted, for at least the 400 years that we have been able to see it. Jupiter is not a world in the same sense that Earth is. It has no solid surface to stand on. It is a gas giant, a colossal ball of hydrogen and helium, the same primordial elements that make up the sun. In fact, if Jupiter had been about 80 times more massive, the pressure in its core would have been great enough to ignite nuclear fusion. It would have become a star. Our solar system would have been a binary star system, and life as we know it would have been impossible. We exist in part because Jupiter was a failed star. Its size is almost impossible to comprehend. Its diameter is 11 times that of Earth. Its mass is 2.5 times the mass of all the other planets in the solar system combined. It is the gravitational anchor of our celestial family. The Sun may be the king, but Jupiter is the prime minister, the powerful vizier, the heavy who dictates the orbits, the fates, and the very existence of all the smaller bodies in its court. And its primary role, the one that has been most crucial to our own existence, has been that of a bouncer, a cosmic gatekeeper. To understand this, we must go back in time to the chaotic, violent youth of the solar system 4.5 billion years ago. The planets had just formed, but they were not alone. The space between them was a thick, soupy, and incredibly dangerous swarm of leftover planetesimals, the building blocks of planets that had failed to coalesce. The early solar system was a cosmic shooting gallery, a hailstorm of stone and ice. The young Earth was in the middle of this chaos. It was being subjected to a constant, relentless bombardment of asteroids and comets, a period known as the Late Heavy Bombardment. This was a process that, while violent, was also necessary. These comets and asteroids were rich in water and organic compounds, and it is thought that this bombardment delivered the very ingredients that would one day allow life to begin. But this period of intense bombardment needed to end. For life to evolve from simple, microbial scum into complex, delicate creatures, it needed a period of relative peace and stability. The cosmic shooting gallery had to be cleared out. And this is where Jupiter, the great protector, played its first crucial role. Jupiter's immense gravitational field acts like a giant cosmic vacuum cleaner, or perhaps more accurately, a gravitational slingshot. As the trillions of comets and asteroids from the outer solar system fell inward toward the Sun, they would have had to pass through Jupiter's domain, and the vast majority of them would have had a close encounter with the giant planet. For many of these icy bodies, this encounter would have been fatal. They would have been captured by Jupiter's gravity and pulled into a fiery, suicidal plunge into its deep, turbulent atmosphere. Over millions of years, Jupiter would have absorbed and continues to absorb countless comets and asteroids, taking the hits that might have otherwise been destined for Earth. But for many others, the encounter was not a direct collision, but a near miss. And in a gravitational interaction, a near miss can be just as consequential. An icy comet falling in from the distant Oort cloud might swing past Jupiter. The planet's immense gravity would grab it, swing it around, and then fling it, like a stone from a slingshot, with a huge increase in velocity. This gravitational assist would be so powerful that it would accelerate the comet to a speed greater than the Sun's escape velocity. It would be kicked out of the solar system entirely, ejected into the vast, lonely expanse of interstellar space, never to return. For millions of years, Jupiter performed this great cosmic cleanup. It was a gravitational bouncer at the door of the inner solar system. It took the chaotic, dangerous swarm of debris from the early days, and it either ate it or it threw it out of the club. Without Jupiter, the models show that the intense bombardment of the inner planets would have continued for much, much longer. The Earth would have been subjected to a rate of large, extinction-level impacts, perhaps 1,000 times greater than what we have experienced. It is unlikely that complex life, let alone an intelligent species like our own, could have ever evolved in such a violent and unstable environment. We are here in part because Jupiter is there. Its immense, silent, and patient gravitational influence cleared the space lanes, creating a safer, more stable neighborhood for our small, fragile world to grow and thrive. It is our shield, our big brother, a silent, distant guardian that has been protecting us since the very beginning. And its work is not over. We have seen, even in our own brief human history, direct, spectacular evidence of Jupiter's ongoing role as the great protector. The role of Jupiter as our solar system's gravitational guardian was, for a long time, a matter of elegant theory and complex computer simulations. It made sense. The numbers worked. But it was a story that played out on a timescale of millions and billions of years, a silent, invisible drama from a long-forgotten past. And then, in the summer of 1994, humanity was given a stunning, terrifying, and profoundly beautiful opportunity to watch the Great Protector in action, in real time. In 1993, a team of astronomers, Carolyn and Eugene Shoemaker, and David Levy were conducting a routine survey of the sky at the Palomar Observatory in California. They discovered something strange, a new comet. But this was no ordinary comet. It was bizarre, distorted, and looked, in their own words, like it had been squashed. It didn't have a single bright nucleus. Instead, it looked like a string of luminous pearls, a celestial necklace of icy fragments, all traveling together on the same path. Astronomers around the world turned their telescopes toward this strange new object, which was named Comet Shoemaker-Levy 9. And as they calculated its orbit, a story of incredible gravitational violence began to emerge. The comet had once been a single cohesive body, a respectable chunk of ice and rock a few kilometers in diameter. But in July of 1992, a year before its discovery, its journey had taken it on a perilously close pass of the planet Jupiter. It had flown just inside the gas giant's Roche limit, the critical distance within which a celestial body, held together only by its own gravity, will be torn apart by the tidal forces of a larger body. Jupiter's immense gravity had acted like a cosmic torture rack. The side of the comet facing the planet was being pulled so much more powerfully than the side facing away that the comet was literally ripped to pieces. It was a silent, graceful, and utterly devastating act of gravitational dismemberment. The single comet was shattered into more than 20 large fragments, which then continued on their new, altered orbit, now as a broken, ghostly train of icy debris. But the story got even more dramatic. The astronomers' calculations of this new orbit revealed a stunning and unprecedented prediction. The comet was not destined to fly off into the outer solar system. Its close pass had so altered its trajectory that it was now on a collision course. In July of 1994, the entire string of cometary fragments was going to slam, one after another, into Jupiter itself. For the first time in human history, we were going to be able to witness a major impact event in our solar system. The world's astronomers prepared. Every major observatory on the planet and the newly repaired Hubble Space Telescope in orbit turned their gaze toward Jupiter. This was not just a scientific curiosity. This was a profound and sobering object lesson. The comet was a cosmic bullet, and Jupiter was about to take the hit for us. For 6 days, from July 16th to July 22nd, 1994, the world watched mesmerized. One by one, the fragments of Shoemaker-Levy 9, some of them more than a kilometer in diameter, plunged into Jupiter's vast cloudy atmosphere. Because of the planet's rotation, the impacts all occurred on Jupiter's far side, just beyond our direct line of sight. But the planet's rapid 10-hour rotation meant that the impact sites would swing into view just a short time later. And what a sight it was. Each impact was an event of almost unimaginable violence. The fragments, traveling at over 130,000 miles per hour, disintegrated in colossal fiery explosions in the upper atmosphere. They created brilliant, searing fireballs that flashed brighter than the entire planet, and superheated plumes of gas from deep within Jupiter's interior were thrown thousands of kilometers up into space. As these impact sites rotated into view, the telescopes of Earth revealed a series of dark, ugly, and utterly spectacular bruises on the beautiful face of Jupiter. They were vast, dark, circular scars, some of them larger than the entire planet Earth. The largest of these scars, from the impact of the fragment designated G, was a dark, complex, multi-ringed splotch over 12,000 kilometers in diameter. It was a wound of planetary scale. For weeks, these dark bruises remained visible in Jupiter's turbulent atmosphere, a string of black eye spots marring the familiar pastel cloud bands. They were a graphic, visceral reminder of the immense energy that had been unleashed. The energy of the largest impact was estimated to be around 6 million megatons of TNT, hundreds of times more powerful than the combined nuclear arsenals of the entire world. We sat here, on our small, blue planet, and we watched a neighboring world sustain an impact that, had it struck the Earth, would have caused a global catastrophe. It would have triggered a mass extinction event on a scale with the one that wiped out the dinosaurs. It would have been the end of our civilization and perhaps the end of our species. But it didn't hit us. It hit Jupiter. The Great Protector had, once again, taken the blow. The Shoemaker-Levy 9 event was a stark, beautiful, and terrifying wake-up call. It transformed Jupiter from an abstract scientific object into a true physical shield, a guardian whose importance to our own survival was no longer a matter of theory, but a matter of observed, spectacular fact. But Jupiter's role as a protector is not just about taking the occasional spectacular hit. Its gravitational influence is a constant, steady, and shaping force, a silent shepherd that has organized the entire architecture of the solar system in a way that is profoundly beneficial for us. Let's go back to the asteroid belt, that vast orbiting junkyard between Mars and Jupiter. Have you ever wondered why it is a belt of asteroids and not a planet? The raw materials were there. In the early solar system, there was likely enough rock and ice in that region to form another terrestrial planet, perhaps one several times the mass of Earth. But that planet was never born. And the reason is Jupiter. The immense gravitational influence of the young, forming Jupiter, was a disruptive, chaotic force in this region of space. Its gravity constantly stirred the pot. It pulled and nudged the small, forming planetesimals, flinging them into eccentric, tilted orbits. Instead of being allowed to slowly, gently, and quietly coalesce into a single, large body, they were constantly being sent careening into each other at high speeds. These were not gentle, constructive mergers. They were violent, destructive collisions. The planetesimals shattered each other, breaking apart into the smaller fragments that we see today. Jupiter's gravity acted as a great cosmic bully, preventing its smaller would-be sibling from ever getting its act together. And this was, for us, an incredible stroke of luck. If a large planet had been allowed to form in the asteroid belt, the gravitational dynamics of the entire solar system would be different. Its influence could have disturbed the orbit of Earth, potentially sending our planet into a more eccentric, unstable path, leading to catastrophic climate swings. Or it could have acted as another gravitational slingshot, flinging a much higher rate of asteroids and comets into the inner solar system. The asteroid belt, the great failed planet, is not a threat. It is, in its own way, another part of our shield. It is a testament to Jupiter's power as a planetary sculptor. The Great Protector not only cleans up the mess in the solar system, it also prevents new, potentially dangerous messes from ever forming. Its influence is subtle and written in the language of gravity. We see it in the Kirkwood gaps, specific empty regions in the asteroid belt where certain orbits are unstable because they would have a resonant gravitational relationship with Jupiter. Any asteroid that wanders into one of these gaps is quickly ejected by Jupiter's relentless, rhythmic, gravitational nudges. It is a quiet, celestial tidying up, a constant, patient act of gravitational housekeeping that has been going on for billions of years, all of which contributes to the long, stable, and relatively peaceful environment that has allowed life on Earth to flourish. It is a silence that we owe our very existence to. We have witnessed Jupiter's power as a shield and a bouncer. We have seen it take a fusillade of cometary blows that would have sterilized our own world, and we have understood how its immense gravity prevented the formation of a potentially dangerous planet in the asteroid belt. It is the great, silent guardian of the inner solar system. But the story of Jupiter's influence is not just one of destruction and prevention. It is also a story of creation, of delivery, and of a strange, chaotic, and beautiful dance that may have been responsible for shaping the very worlds we know today. To understand this, we must go back once more to the very beginning, to the first few million years of the solar system's life. The sun is a young, hot, and active star. The planets are not yet in their final stable orbits. They are still forming, embedded in a vast spinning disk of gas and dust. This is the primordial solar nebula. And in this early, chaotic era, Jupiter was not the stately, distant king we know today. According to a new and powerful theory known as the Grand Tack, Jupiter was a wanderer. The theory begins with Jupiter forming further out in the solar system, where the abundance of ice allowed it to grow into a colossal giant. But as it grew, it began to interact with the thick, soupy gas of the nebula around it. This interaction created a drag, causing the young Jupiter to lose orbital energy and begin a slow, majestic, and terrifying spiral inward toward the Sun. For hundreds of thousands of years, the great giant migrated, its orbit shrinking, its immense gravitational influence plowing through the inner solar system like a great celestial snowplow. This inward journey was a period of profound creative destruction. As Jupiter moved, it would have scattered the smaller, rocky planetesimals that were trying to form in its path. This may explain one of the enduring mysteries of our solar system: the small size of Mars. The red planet is a lightweight, a planetary runt, only about a tenth of the mass of Earth. The old models of planetary formation struggled to explain why Mars was so small, when it should have had plenty of raw material to grow into a much larger world. The grand tack theory offers a beautiful and violent solution. As Jupiter tacked inward, its gravity would have swept through the region where Mars was forming, stealing or ejecting a huge portion of the available building blocks. Mars, in essence, was starved at birth by the passage of its giant, greedy sibling. It is a small planet because Jupiter, in its wandering youth, ate most of its lunch. This inward migration would have continued, and Jupiter could have become a hot Jupiter, a gas giant orbiting perilously close to its star, a common configuration we now see in many other solar systems. Had this happened, its immense gravity would have likely ejected Earth and the other inner planets from the solar system entirely. But it didn't, because Jupiter was not alone. Just behind it, the second great gas giant, Saturn, was also forming. And as Jupiter migrated inward, Saturn was also slowly migrating inward behind it. Eventually, the two giants fell into a perfect, resonant orbital lock. For every 2 times Jupiter orbited the Sun, Saturn would orbit exactly 3 times. This gravitational resonance created a stable, powerful partnership. Saturn's own gravitational pull began to tug on Jupiter, counteracting the drag from the nebula. The inward spiral stopped, and then, miraculously, it reversed. Locked together in this gravitational dance, the two great giants, Jupiter and Saturn, began to migrate outward again, away from the Sun. This is the tack, like a sailboat changing direction in the wind. They moved back out through the solar system, eventually settling into the stable, distant orbits we know today. This grand tack, this great inward then outward journey of the gas giants, would have been the single most important and formative event in the history of our solar system. It was a brief, chaotic, and world-shaping ballet. And it may be the reason we are here at all. Because as Jupiter and Saturn tacked back outward, their immense gravitational influence would have once again churned the contents of the solar system. Their journey would have scattered the contents of the outer asteroid belt, a region rich in water-bearing asteroids and comets. It would have flung trillions of these icy bodies in every direction, and a small but significant fraction of them would have been thrown inward toward the hot, dry inner solar system where the Earth was forming. This is the second, more subtle, and profoundly creative aspect of Jupiter's role as a protector. It is not just our shield, it may also have been our water bringer. The young Earth, forming so close to the Sun, was likely a dry, barren, rocky world. It was too hot for water ice to condense here. So where did our magnificent, life-giving oceans come from? They were likely a gift delivered by a fusillade of icy asteroids and comets, flung our way by the gravitational chaos of Jupiter's great wandering journey. Jupiter, in its role as a cosmic shepherd, first cleared out the dangerous, large debris, and then, in a beautiful act of cosmic generosity, it delivered the very water that would one day fill our oceans and become the cradle of life. It is a story of incredible, beautiful, and contingent luck. If Jupiter had not migrated inward, Mars might be as large as Earth. If Saturn had not been there to catch it and pull it back out, Jupiter might have consumed the inner planets. If their outward journey had not scattered the icy asteroids in just the right way, Earth might have remained a dry, dead rock. Our very existence, the blue of our oceans, the size of our neighboring planets, the relative safety of our orbit, all of it may be a direct consequence of this ancient, silent gravitational dance, a grand, chaotic ballet performed by the solar system's 2 largest players. Jupiter, then, is not just a simple, static guardian. It is a complex, active, and profoundly influential sculptor. Its story is woven into the very fabric of every other world in this system. It is the bully that starved Mars. It is the bouncer that cleared the lanes of dangerous debris. And it is the generous, if accidental, benefactor who delivered the gift of water to our young, thirsty world. But its influence doesn't end there. Even today, in its stately, distant orbit, its gravitational hand is still at work, shaping the solar system in subtle and powerful ways. It has become the shepherd of a vast, strange, and beautiful collection of celestial objects. These are the Trojan asteroids. Imagine you are looking down on the solar system from above. You see the sun at the center and the great, almost circular path of Jupiter's orbit. There are two special points in this orbit, two places where the gravitational pull of the sun and the gravitational pull of Jupiter are perfectly balanced. These are the Lagrangian points, L4 and L5. One of these points travels 60 degrees ahead of Jupiter in its orbit, and the other travels 60 degrees behind it. These are islands of profound gravitational stability, and over billions of years they have become the gathering places for a vast swarm of asteroids. There are two great, cloud-like collections of primordial rocks, one leading Jupiter, one trailing it, like two great flocks of sheep being herded by a gravitational shepherd. There are over 7,000 known Trojan asteroids, and there are likely millions more, too small to be seen. They are time capsules from the birth of the solar system. Because they have been trapped in these stable, gravitational sweet spots for eons, they have not been subjected to the same level of collisions and solar heating as other bodies. They are some of the most pristine, untouched, and ancient material in our entire celestial neighborhood. Jupiter, the great protector, has not only shielded us, it has also preserved for us a perfect, untouched museum of our own origins. Two great, silent, orbiting libraries of primordial rock, waiting for us to one day visit and read their secrets. The story of Jupiter is a story of nuance. It is not just a shield. It is not just a vacuum cleaner. It is a force of chaos and of order, of destruction and of creation. Its immense, silent presence has dictated the history of every world in this system. It is the author of the asteroid belt, the architect of Mars's small size, the delivery system for our water, and the patient keeper of our most ancient history. To understand Jupiter is to understand that we do not live in a solar system of 9 separate, independent planets. We live in the solar system of Jupiter, and we are all just lucky enough to be along for the ride. We have traced the grand, gravitational story of Jupiter, our solar system's bouncer, its sculptor, and its accidental benefactor. We have seen how its chaotic, youthful wanderings may have starved Mars, created the asteroid belt, and delivered the very water that fills our oceans. We have witnessed its raw power in the spectacular, fiery death of a comet. But the story of Jupiter's influence does not end with its gravitational might. To truly understand its character, we must journey close to the planet itself through its own miniature and surprisingly violent solar system. We must brave the invisible, lethal realm of its magnetosphere. Let's return to our small, sturdy spacecraft. We are leaving the relative safety of the outer solar system and beginning our final, close approach to the great striped giant. As we get closer, our instruments begin to detect something that is not visible to our eyes: a force. A vast, powerful, and incredibly dangerous bubble of magnetism, extending for millions of miles around the planet. This is Jupiter's magnetosphere. Like the Earth, Jupiter has a molten metallic core that generates a powerful magnetic field. But the scale of Jupiter's field is almost beyond comprehension. It is nearly 20,000 times stronger than Earth's, and it is the largest and most powerful single structure in the entire solar system, after the Sun's own heliosphere. If it were visible to our eyes, it would appear larger in our night sky than the full moon. And this magnetic field is a trap. It is a vast, invisible net that sweeps up the charged particles of the solar wind, accelerating them to incredible speeds and trapping them in intense, swirling bands of radiation. These are the Jovian radiation belts, and they are 1,000 times more intense than the Van Allen belts that surround the Earth. They are, without a doubt, the most hazardous and lethal environment in the solar system, outside of the Sun itself. To fly a spacecraft or a human through these belts is an act of profound, calculated risk. The high-energy electrons and ions trapped here are like a constant, silent, and invisible storm of microscopic bullets. They would tear through an unshielded astronaut in seconds. They would fry the delicate electronics of a spacecraft, causing catastrophic failures. The engineers who designed the Pioneer, Voyager, Galileo, and Juno missions had to armor their probes, placing their sensitive electronics inside thick titanium vaults just to survive a brief passage through this invisible inferno. This is the fierce, protective, and deeply inhospitable nature of our great guardian. It shields us from comets, but it has created a local environment around itself that is almost pure, weaponized radiation. It is a king who has surrounded his castle with a moat of invisible fire. And the source of much of this deadly radiation is one of the most fascinating and volcanically active worlds in the entire solar system, Jupiter's small, tormented moon, Io. As we navigate the treacherous radiation belts, we can see Io. It is not the familiar, gray, cratered face of our own moon. Io is a world painted in the shocking, lurid colors of sulfur, brilliant yellows, angry oranges, deep reds, and stark volcanic blacks. It looks less like a moon and more like a diseased, cosmic pizza. And it is, without a doubt, the most geologically tortured object in our celestial family. Io is locked in a constant gravitational tug-of-war. It is squeezed and stretched by the immense gravity of Jupiter on one side and by the rhythmic, regular pulls of its neighboring moons, Europa and Ganymede, on the other. This constant tidal flexing heats the moon's interior to an incredible degree. It is a process of perpetual gravitational kneading, and it turns the small moon into a raging volcanic hellscape. Io is covered in over 400 active volcanoes, but they do not spew molten rock. They spew molten sulfur and sulfur dioxide, blasting great, umbrella-shaped plumes of gas and dust hundreds of kilometers up into space, where there is almost no atmosphere to stop them. And this is where Io feeds the great deadly beast of Jupiter's magnetosphere. These volcanic plumes eject over a ton of sulfurous material into space every single second. This material is captured by Jupiter's magnetic field, where it is ionized, its electrons stripped away, and it is accelerated to form a great, swirling, donut-shaped cloud of superheated plasma that encircles the planet. This is the Io plasma torus. It is this cloud of volcanic moon dust that provides the raw material for Jupiter's ferocious radiation belts. The most violent place in the solar system is not a planet. It is a moon, tormented by its parent, that is constantly spewing its own guts into space, feeding the great invisible monster of radiation that surrounds them both. It is a complex, violent, and strangely beautiful system, a family of worlds locked in a dance of creation and destruction. And so our picture of Jupiter is now more complete. It is not just a simple, static shield. It is a complex, dynamic, and often violent system. It is a failed star, a gravitational bully, a cosmic snowplow, an accidental water bringer, a patient shepherd of asteroids, and a fierce, radioactive king, fed by the volcanic anguish of its own moon. It is a world of profound contradictions. Its existence is likely the reason that complex life on Earth was given a chance to flourish, and yet its own immediate environment is one of the most hostile and life-destroying places we know of. It is our protector, and it is a monster. As our imaginary spacecraft finally pulls away, as we leave the realm of the giants and begin our long, quiet journey back to the small, gentle, and welcoming blue of our own world, we are left with a feeling of profound and humbling gratitude. We are here because of a series of ancient cosmic accidents. We are the beneficiaries of a chaotic, gravitational ballet that we are only just beginning to understand. We live in a quiet, protected neighborhood of the solar system, a small, safe harbor in a much larger and more violent cosmic ocean. And we have Jupiter to thank for that. The next time you are outside on a clear night and you see a brilliant, steady, star-like light in the sky, brighter than all the others, know that you are not just looking at a planet. You are looking at your guardian. You are looking at the great, silent, gravitational shield that has protected our world for billions of years. A shield that has taken the hits for us, that has cleared our path, and that has, through its own chaotic journey, perhaps even given us the very water we drink and the air we breathe. It is a silent, distant, and unassuming king. But its influence has shaped our past, it protects our present, and it will continue to guard our future, long after we are gone. It is the great, steadfast, and beautiful protector. and so our journey to the King of the Worlds comes to an end. Jupiter's story is a profound reminder that the universe is a complex, interconnected system, where the actions of a distant, giant world can have the most intimate and life-giving consequences for a small, blue one. We are a part of a great cosmic family, and we are lucky to have such a powerful older sibling looking out for us. I hope this journey to our great protector has brought you a sense of safety and wonder. May it remind you that even in the vastness of space, we are not alone, and that we are protected by silent gravitational forces we can barely comprehend. May your rest be deep and peaceful. Until next time, sleep well.